We have a lambda A is 2, lambda S is 1, MM3 that starts at 4. We let t be the first time q is no longer in state 4, and we ask, what is the distribution of t? Secondly, we ask, what is the probability that when the q does first change state, it will be to state 5 instead of state 3? To solve this problem, we first note that all three servers are busy. If we let TSI be the time for the I server to complete his or her service, for I is 1, 2, 3, and we let TA be the time for the next arrival, then all of these are independent, and the time to change state, which is what we're after, T, is just the minimum of these. So it would change state when either server 1 completed, or server 2 completed, or server 3 completed, or there was an arrival. But since these are independent exponentials, exponential stability holds. And exponential stability says the minimum of these is just an exponential with the sum of the rates. So it would be 1 plus 1 plus 1 plus 2 for the arrivals. In other words, 3 lambda s plus lambda a, which is 5 exponential. So that answers the first question. The second question that we have is, what is the probability the next state would be 5? That really means that an arrival comes before the first service. So we're asking, what is the probability that TA, the arrival time, is less than the minimum of all the servers? So the minimum of T1s, T2s, and T3s. Well, once again, exponential stability applies to these three serving times. And so since each one of them are 1 exponentials, the minimum of these three is a 3 exponential. So what we're really asking is, what's the probability that a 2 exponential comes before an independent 3 exponential? And so we find that by the joint distribution, which we find by multiplying the exponential PDFs together since they're independent. And then we have to integrate y for the servers from the time that the arrival occurs to infinity, so t to infinity. And then on the outside, well, the arrival could occur at any time, so we have to go from 0 to infinity. So we have the integral from 0 to infinity dt, the integral from t to infinity 2e to the minus 2t, 3e to the minus 3y dy. Well, this inner integral can be moved to isolate the y, and then we can recognize, well, that's just reliability. This is just the reliability of the three servers at time t. So we know that's just e to the minus 3t. And so what we really are left with is an integral from 0 to infinity of 2e to the minus 2t, e to the minus 3t. And of course, those could be combined to come up with e to the minus 5t. And then we could multiply and divide by 5 to get 2/5 the integral from 0 to infinity of 5e to the minus 5t dt. But this integral is just integrating over the 5 exponential PDF, and so it's 1. So the answer is 2/5. The last thing to note is that this 2/5 is the ratio of the increase, or i.e. going to state 5, over the rate of doing anything that's changing states, which is what you would expect when you have a Markov chain.